Operating theatres are full of electronic equipment, things like infusion pumps, monitoring devices, patient heating, surgical diathermy, and all of them require the patient to, in some format, be in contact with an electrical piece of equipment. And therefore there's the risk of getting harm from the electrical circuits, either through burns or through shocks that can range from muscle spasm and pain all the way up to a cardiac arrhythmia. So it's important that the electrical equipment we use is safe, and you have to be able to explain in the exam how those machines are made to be safe. So the risk of harm happens anytime that there is a voltage that a patient or a member of staff is exposed to. If there's no voltage, then no current can flow, there's no risk. But as soon as you have a voltage or a potential difference, that means electrons want to move from place A to place B, and they will go through what they need to get there depending on how big that voltage is. And so if our patient or a member of staff becomes part of that journey, then they're at risk of getting harmed by the electrical current. So for the exam, there are 3 classes of electrical equipment that you need to be able to describe, depending on how they are set up to protect people from getting an electric shock. So we have class 1 equipment. Now this is the simplest, and it's essentially, it has some insulation to stop you touching the live parts, the live wires, and then it has a metal casing which is connected to earth in some way. The idea being the electrons will go the path of least resistance. If the insulation breaks and those electrons can get out, they will preferentially go through your metal casing into the ground rather than through the patient or the member of staff, because your skin, your body is much higher resistance than a metal wire and a metal case. So hopefully all of those electrons will divert down the easier route and you won't get an electric shock. That is class 1, and it's the simplest. And this is generally in older machinery, things like old monitors and old surgical lights. Class 2 equipment is double insulated, which more people have heard of. And this essentially means you've got double the insulation, and therefore even if one layer of insulation fails, you've got another one, and therefore you don't need an earth because you're never exposed to the live components. And that's how they are safe. It's just double wrapped, so you're less likely to end up touching anything that is harmful. And class 3, rather than protecting you from a high current, simply makes it a very low current, so that even if you do touch it, it's not going to do you much harm. So these are devices that run off very low voltage, usually off a battery, so that even if you touch something that's live, it's not going to have enough voltage to overcome the resistance of your skin, and it won't give you an electric shock. So things like torches, headlamps, some monitoring devices. But the key is they each have a symbol. That symbol will tell you what class it is. What you actually do about this is, if there's an evidence of a fault, you're going to report it to estates. You're not going to fix it yourself. You're not going to need to know anything more than that. Being aware of the different classes of equipment is all you need to be able to save the exam. So as with everything in medicine, we set it up in a way to be as safe as possible, but we expect that it can still go wrong. So we put in backup mechanisms that will kick in if our primary fail-safe fails. So even if you do get a short circuit or a problem or a breakage and an exposed live wire, there are other things within the circuit built into the machinery that will provide even more protection for the staff and the patient. And the 3 we're going to talk about are residual current devices, line isolation monitors, and equipotential earthing. Residual current devices essentially monitor how much current is passing through the circuit, and if it drops below the expected level, because some of that current is leaking somewhere it shouldn't be, like through a patient or through a member of staff, then it immediately breaks the circuit and stops the current from flowing at all. And it can act within milliseconds, so that even though some current is technically passing through the patient or the member of staff, it kicks in so quickly that it's not enough current to do substantial harm. So they detect leak current, and then they break the circuit to stop that current from flowing. Line isolation monitors won't intervene, but they will let you know that there's an issue. So these generally monitor systems where there's no direct earth connection, and if a situation occurs where there is potential for a current to leak through to earth or to pass out of the casing or through the insulation, it will sound an alarm and allow you to intervene and to fix it. So it's a monitor and a smoke alarm kind of setup. It's not going to actually intervene and take the risk away. It will just alert you to it. So that's a line isolation monitor. And equipotential earthing is a simple idea, which is if you don't have a potential difference, then no current is going to flow. So equipotential earthing connects all the metal surfaces in your operating theatre to the same reference bar, which means they are all at the same potential, which means there's no current that could flow between the two. It's sort of like preventing a buildup of static electricity and then getting a shock. It's preventing there being any potential difference between all the metal surfaces so that there's no chance that a current can flow from one to another and someone can get shocked. That's equipotential earthing. So that's how electrical systems prevent electrical shock from a main supply. They can also be classified based on how much leakage current they will allow. So some systems are set up in a way that a tiny amount of leak is acceptable, depending on the scenario, but they are classified differently depending on the scenario in which they're being used. And there are 3 types you need to be able to name. They're type B, type BF, and type CF. And this is a separate classification from the class 1, 2, and 3 that we talked about with regards to whether they're double insulated, earthed, or just really low voltage. The leak current, the B, BF, CF, is a separate classification. So you can be class 1 BF, or you could be class 2 BF. So they will often have 2 icons to denote which categories they fall in. The thing to know is the 1, 2, 3 is how it prevents a mains supply shock, and the letters tell you what the maximum leakage current that is allowed for that piece of equipment. So B stands for body, and this is for anything that is external to the patient but is touching the patient's body, and a classic example is your ECG electrodes or ultrasound probes. They are physically touching the patient, but they're not directly in contact with a high-risk conducting tissue such as the heart itself. And these can have an allowable leakage current of anywhere up to 500 microamps, depending on where they're being used and what they're being used for. And so these machines that are classified as B or body are safe to touch the patient, but they're not safe to be directly in contact with a high-stakes conductive tissue such as the heart. BF stands for body floating, and the floating refers to the fact that the electrical equipment has usually double insulation, so there's less risk of a leak current in the first place. And these are things like your infusion pumps that are directly connected to the patient's vein. And so BF have a stricter criteria, and so they are smaller leakage currents are allowed, usually less than 100 microamps. And CF stands for cardiac floating. These are the highest risk ones. There's things like internal defibrillators or invasive arterial blood pressure monitors, which are directly connected through a column of fluid from your transducer to your heart. Or the diathermy, when a cardiothoracic surgeon is using diathermy in the thorax, there is a direct connection to the heart. So these are the highest risk, the most stringent. The smallest leakage current is allowed between 10 and 50 microamps. So these are the most stringent criteria because you are very close to or in direct contact with the heart. So any leakage current is much higher risk because it's more likely to induce an arrhythmia. So why not just make everything CF? Because then that's safest, surely. You don't need to. It's massively over-engineering things that's going to cost more, make it impractical to use. So you don't need to have those criteria and those tiny, tiny leak currents if you're not going anywhere near the heart. So for an ultrasound probe on the leg, it doesn't matter if there's a tiny leak current of, say, 70 microamps, but it is a big deal if a diathermy leaks 30 microamps of current when operating near the heart. So there's different layers for the different equipment being used. You don't need much more detail than that for the FRCA exam. Hopefully that clears it up a little bit.